Hi everyone, here's Wintel, and here's my final project. It's about kind of enhancing the layer ML control with learnable durable update. So basically, for a normal task, for current motion planning control task, we always try to use layer control, which we have a reference trajectory and follow up with some kind of controller. And here's some problem with it. So we know that the layer control is decoupled, and this will lead to mismatch between the planned and executed trajectory, which means that for a planning trajectory, we might cannot execute it at the same as what reference trajectory provide. So I think my question raised up here is, can we tightly couple planning and execution to achieve more convergent and stable behavior, which means can we let the agent strictly follow up the reference trajectory? So what we do is for the related background, we use some layer control architecture. Some of people use it in a kind of a multi-rate control optimization decomposition. And also because we use reinforcement learning in this project. So theoretically, reinforcement learning, which means layer reinforcement learning, will also be used in kind of complex dynamic system. And also some goal condition RL, kind of a layer RL is used here for later on improvement. So what we do here is we are calling to Young's work and Martini. What we do here is we jointly train the planner and controller with a neural network to align the reference and execution, which means for kind of things, we are kind of initialize the reference trajectory, and we added a dual variable to this reference trajectory, which means a kind of a learnable dual variable. And with this kind of a fine tune or with this change, the reference trajectory will be more executable to follow up, which means after this controller, we will follow up like what his reference looks like. And but this has some kind of a bad behavior because there are some slow convergency, limited scalability, and complexity of the RL dynamics. What we do here is first we introduce the supervised learning instead of our overall reinforcement learning for the durability because it's kind of a simple network. And what we do is gathering the data and construct the new loss for the durable, and we will induce faster convergency and more stable learning and basic for the better scalability. And then for the transformer-based, and also second would be we incorporate transformer-based durable learning with the actor creating network and also the neural network because it's kind of sequence where we introduce the reference and where outcome would be kind of the reference durable and also the kind of action. So here's quite fits to the transformer model, which could help our scalability. So now would be kind of a method. How do we use exactly? So first, we will find out the problem. We will kind of generate a kind of a tracking policy at the end. But also initialize, we will try to use A star or RT to find out reference trajectory, where we use a plain policy over here. And the first improvement would be supervised neural network learning. First, instead of using the RL to have neural network, we will use supervised learning. We will collect data during the rollout and compute the correction as a difference between the reference and the executed trajectory. This is what instability and slow convergence of RL. And the second improvement would be transformer architecture integrate in the active network and also the neural network. This will use attention-based models to improve the ability to learn long-term temporal dependency. This will allow to help the model generalize better, and especially in the dynamic environment. And the environment setup. So basically, we use kind of a unicycle model, and there's two baselines. The first is IOQ controller without is kind of naive controller without any durable optics. And second would be the original Young's work and what we improve on them. And what is a problem looks like is basically depends on what the rewards. There's three rewards: go, the reference, the smoothness. Which means we have a new step, we have new execution, and how do we evaluate? We evaluate through go, through the reference, through the smoothness to make sure that that action is good enough. What is results look like? So basically, we have two results that could compare. Which first is we only compare the supervised learning compare with RL baseline. Second would be we will compare the transformer-induced architecture with the original baseline. So in the first table, we compared the two methods, and we could find out that for the baseline, IOQR baseline, our method will improve a lot. And also, it's better compared to the Young's one, where we only tracking variable is only 0.012. And also, the training episode, we could say the Young's use kind of tons of training transaction, which is 600,000 transitions, where we only use such a smaller one. We have better convergency and better performance based on that. But after we compare about transformer, we could say that the transformer will induce larger error over here. Our baseline is only 0.01, but transformer we induce 0.06 in this kind of cases. And even with more training iteration. So what we do here, I think, is basically we do not have sufficient data. And also may require more extensive training and a larger data set based on transformer IO. And we are introduced complexity without guaranteeing performance gains. So here's a kind of conclusion. Summary would be, this product introduced main innovation. And our experiments show that supervised learning is not only easier to train, but also outperforms reinforcement learning in both accuracy and convergence speed. This is a promising direction, especially in the application where stability and data efficiency are crucial. But transformer might not be useful because we do not have enough data. We don't have enough training time and longer training resources. So I think first we can combine the supervised learning and transformer together. And also second would be because we use TD3 currently, we might use some simpler AI algorithm like PBO or other kind of things to increase the convergence and robustness. Finally, we will think about test our framework in more complex, realistic settings where generalization matters more, for example, the multi-agent or uncertain environment. And here's our reference. Thanks for you'll be here. And any question, just feel free to email me. Thank you.